Hello everyone and welcome to this course of hands-on deep learning using MatConvNet. So in this first session we're gonna cover a couple of interesting topics like how to do inference with AlexNet and LaNet, and we're gonna also see how to do training with those networks in different datasets like MNIST and Cypher10. But first of all, I'm going to introduce you to how to install the library. So this is MatConvNet. Okay, I assume you have downloaded this version from the website of the course. And the first thing to do is to edit this make file. So here we have a couple of options we have to set up. As for instance, the GPU, if we are going to use CUDA and cuDNN. Let's assume we don't have a good GPU with CUDA and we don't have cuDNN either, so we will leave these two variables empty. We also need to set up like the architecture of our system. In my case I'm using Linux 64, so I'm gonna leave glnxa 64. If you are using Mac or Windows you need to change this. Okay, so probably the most important thing is to set up the path to MATLAB. In my case I have MATLAB here, or at least I think so. Let's check it. Nope. Okay. And now we're gonna compile the library. Don't care too much about the warnings. It usually complains about the version of GCC. Just gonna check if everything is in its place. Yep, it has compiled everything. Good. So we are ready to go. Okay. Now it's time to start with the session. So we have MATLAB, at least 2013 version or higher. We have MatConvNet installed, already compiled. And in order to start, we go to the folder sessions. Okay. Here we also have the instruction for installing MatConvNet. The different folders contain things that we are gonna need for the course. So, for example, the data folder has different pre-downloaded databases like MNIST and Cypher10, and a nice picture of a dog. We have some dependencies like VLFit for some visualizations. We also have pre-trained networks like a pre-trained version of AlexNet and a pre-trained version of LaNet and BEF. Session 01 is contains the main script of the session. So we're going to be following the script of session 01. Okay. The idea is to start like running the script line by line and analyzing what's going on, what's happening, stopping for a while, playing a little bit with variables and the different data structures. Yeah, checking the code. So we're gonna be doing during the session 1. So we're gonna start by running this command, which basically tells MatConvNet to add to set up the paths to the proper with the proper to set up the MATLAB variable with the proper path. So okay, and now we're gonna load AlexNet. AlexNet is a very famous network. We have pre-training already on MatConvNet. Yeah, here we have AlexNet. So you see that so far AlexNet is just a MATLAB structure that contains layers, classes, and normalization. So layers is the structure of the network itself, while classes is a sort of meta parameter defining the names and the description of each of the classes that were used to train AlexNet. So for instance, oops. Yeah, the first class is a Tinka, whatever that is. The second one is a goldfish. Okay. Anyway, so you can have a look to the layers here. We see it has like 21 layers. We have a look to the first layer, which is a convolution. Okay, we will see more about this later. I would like to clarify that in MatConvNet there are two ways of creating networks, or two different APIs for creating networks. The traditional one is called the simple net, and is basically using a MATLAB structure like this one. But then currently people use what is called a DAG net, so directed acyclic graph. So that network is much more powerful and flexible and allows to do many cool things. So the idea is to move all the previous networks like this one and convert them to DAGs all the time. And every time we define a new network, we're gonna define them already as a DAG network. So during the whole course, we're gonna be working with the DAG version of the networks. So in this way, I will show you how to work with the modern API. So okay, we have loaded AlexNet. Since we're gonna convert AlexNet from its like MATLAB structure version, so the simple net version, to the DAG, we need to copy the meta parameter, the metadata, because the conversion script doesn't take into account the metadata. So in other words, we need to save the classes and the description and so on, because we need to use them later for doing inference. So okay, let me do that. I copy the classes from the AlexNet structure, and now we convert it from a MATLAB structure to a MATLAB object, to a DAGNN object. So if we check now AlexNet, you see that now it says that AlexNet is a DAGNN object. So a directed acyclic graph network, and it contains several members like layers, bars, params, meta, model, and so on. So let me tell you a little bit about these properties. So layers is, as before, the definition of the layers of the network, but now it had changed a little bit. So now you have you have like more parameters. You have the name of the layer, okay, the input to that layer, so that's gonna relate like inputs with outputs. So like this layer is expecting the input from this other layer that has this name, and it's gonna produce this output. So then the next layer is gonna be expecting its input to be this output. Okay, then params are the parameters of this layer. So in this case, this is a convolution, so we are talking about the filters and the biases. So this means that this network is going to be keeping the filters, the weights for the filters and for the bias in like these fields. So COM1F and COM1B. We will talk now about this. Then this layer receives like only one input. Okay. Sorry, it receives the input called input, which has index 1, and it produces its output called x1, which has index 2. This indices serves to access this second field called bars. I will explain now what bars is. Then the indices for the parameters, and this is useful for indexing the structure params, are 1 and 2. So in the first two positions of the structure params, you can find the actual weights and biases of convolution 1. Then in block, we see the actual definition, the actual geometry of the network of the convolution layer, which is it's an 11 by 11 kernel, and it's connecting a 3-channel map to a 96 channel maps. So it takes as an input 3 channels and it's gonna produce 96 output channels, or a feature map of 96 dimensions. It has a bias, it has no padding, and it has a stride of 4 by 4. That means that every time we apply the kernels in a convolutional way to an image, so the sliding window is gonna skip like 4 pixels in horizontal and 4 pixels in vertical before applying the next kernel. So it's a convolution in a sliding window way, but skipping some pixels. Okay, so we have already converted the DAG, the network to the DAGNN format, which is more useful, and we have seen how layers the structure looks like. But there are also other very important fields, like for instance bars. So in the theory session we mentioned the concept of blob. Okay, blob being like the data, so the input data as a mini batch is a blob, and the intermediate results that each of the layer is producing during the forward and the backward steps are also blobs. So usually blobs have 4 dimensions, are a 4-dimensional structure, multi-dimensional array or tensor with 4 dimensions. So the first 2 dimensions are height and width of the image. Third dimension is the number of channels or the number of features of that data. So like 3 channels or 96 features. And the 4th dimension is the number of images in the mini batch. So if you select that your mini batch is gonna contain 10 images, so yeah, you're gonna have like the last dimension is gonna be 10. So MatConvNet provides us with a structure called bars, okay, that will contain all these blobs. So when you are doing forward or backward propagation, the intermediate results along with the input and the labels, the output labels and so on are going to be stored here in bars. So bar 1 will be containing like the input data, and bar 2 will be containing the output of the convolution 1, x1, if you remember before we saw that. Bar 3 will be containing the output of ReLU 1, and so on and so on. So every time you need to check for the results, for partial results, you need to access the bar field. Then we have params, which are basically the parameters of the network. So the actual place where the weights and the biases are stored. So we see the first member of params is convolution 1 F, so the filters of the convolution 1, and the second member is like the biases of the convolution 1. Then we have the filters of the convolution 2, bias of the convolution 2, filters of convolution 3, and so on and so on. We can check the size of these guys. Okay. We can actually access to these guys, but it's gonna be massive. But it makes more sense usually to check the size of the guys. So it's a 3x3 kernel that expects 256 dimensions, and it produces a map of 384 dimensions. We can do many things with this, like we can check the minimum value of the kernel, the average, and so on and so on. So the average of this is very close to 0. Maximum 0.46, yeah, and so on. So let's continue with the script now that we know a little bit more about the structure of a network. So remember that before we were converting AlexNet from its standard simple net structure as a MATLAB structure to a DAGNN object. We copy something called classes description. So now we have to assign it back in order to keep it for a later inference process. Okay. So there is quite a cool feature here that we can use it to show the network, and it's called print. The method print helps to like have a look to the definition of the net. So max number of columns 5 is just to say that when you are plotting this, we only want to see 5 columns in a row. So here we see that the structure of AlexNet is like one convolution followed by a ReLU, a local constant normalization, a pooling, second convolution, ReLU, normalization, pooling, convolution 3, ReLU, convolution 4, ReLU, convolution 5, ReLU, pooling, and then fully connected layers, ReLU, fully connected layer, ReLU, fully connected layer H, which is the classifier already, and then a softmax. Here, these are like the dimension of, this is the description of the variable bar, but in this case, since we haven't passed through any data, everything is set up to none. So if we do some inference, then here we will see like what are the sizes of the input images, the intermediate results, and so on. Cool, right? You also see how many parameters that this take. Okay. Now we can visualize filters. This is something quite cool usually. Filter visualization of the different layers. So we're gonna be focused on layer 1 because it's usually the one with more like distinctive things like filters and so on. Yeah, so you don't need to run this script through until the end, so probably it has already computed the first layer, so we can just stop it and have a look to the results. So this script basically takes a network, it's gonna produce a folder like the folder that you indicate here, result/filters AlexNet, and it's gonna copy the result of the visualization of the filters there as PNGs images. So we can actually go inside, go to layer 1 for example, and have a look to the filters. So look how the filters are looking for like oriented high contrast so high frequencies. So you see it's looking for high frequencies in like different directions, but you also see blobs. Yeah, we have to admit that they look quite cool, actually. They don't look so cool for the networks. For instance, if we work with I don't know, for example, BGF. Remember that we need to convert BGF to the appropriate DAGNM format. Okay. Have a look. Yep, that's a DAGNM, and we can now visualize its filters. See that these filters are a bit more like blobs. I think this might have to do with the differences in the architectures. So like having a different depth, number of channels and so on. During the training, perhaps BG has to try to get the best accuracy it can in a slightly different way. So it's distributing the feature extraction process in a slightly different way. First it focuses on blobs and then moves to something else, while AlexNet kind of start using edges and then move to blobs and so on. I don't know, I have no idea, but this is quite curious. It will be worth it to spend some time finding out why this is going on. One thing you might observe here is that several of the kernels look alike. So this kernel and this kernel are quite similar actually. So yeah, this might happen when we are training convolutional neural networks. We try to break the symmetry of the kernels. That means that we try to have different kernels like triggering to different inputs in a different way. So we would like to have like the kernels to be as different as possible, so focusing on different aspects. But sometimes what happens is that the initialization of the convolution layer, of the different kernels of the convolution layer, is probably too similar, or even though they are not too similar, they end up converging to the same sort of solution and they become redundant. So this is a bit problematic, and the idea would be like to erase one of these guys or to perturbate it a little bit to try to make it convert to some other things, which is probably more interesting for the recognition process. But anyway, we'll talk more about this later. Okay, so what if we start doing inference with AlexNet? So this is gonna be the first contact with an inference method for deep learning. So we have loaded an image. We're gonna have a look. Yep, it's a nice dog. And AlexNet is gonna tell us that this is a dog, hopefully. So we call the inference classification method with the image and the network. Woohoo! It says this is a golden retriever, which is one of the subclasses of dogs. Yeah, it's correct. This is the confidence that the network has about this being a golden retriever, which is almost 0.6, sort of high. Yeah, the network is quite sure this dog is a golden retriever, which is quite amazing result. in my opinion. Well, anyway, let's gonna have a look to the inference code. So how to do inference for classification. It's actually quite simple. So this script receives an image, okay, and a network. And the first thing to do is to normalize the image. So we need to normalize the image in order to make it as similar as possible to what the network is expecting. So during the training, the database using for training was normalized in a specific way, and in order to get the best result we can, we need to normalize our images for testing in a similar way. So the first thing to do is to convert the image from a standard integer representation to single. Okay, usually in MatConvNet we're gonna be always working with singles, especially in GPU. Then the second step is to resize the image to the size expected by the network. This is specified in the meta parameters, so that's why we copy the meta parameters from the MATLAB extractor to the DAGNN at the beginning. Okay, so we only need to resize like the spatial dimensions, so width and height is stored here. And afterwards we need to do zero mean, so we need to remove the mean of each of the RGB channels according to what we computed during training. So in training, when we perform training, we take the whole training data and we compute the mean of all the images, and then we do that per each of the channels, and we keep that in order to apply it later to new incoming images. So this is what we are doing here. We are removing the mean of the image. We are moving the mean of the training image, the training set, to this image. I hope the concept is clear. Okay, once we have done this, the only thing we need to do the inference is to call net.eval with this cell array. So this cell array is basically a name and the data. So usually when we use cell arrays in MatConvNet, we also need to define like a name for that for each of the fields contained in the cell array. Okay, in this case, to call it input is not arbitrary. So the network has the first network of the blob is called input, and we saw that before, right? Do you remember when we were checking AlexNet.bars, which is where the blobs are contained? The first blob was called input. So the network is expecting to start the process by something called input. So that's why we need to use this name here. And then the network expects to finish the process with something called prop from probabilities. We can also see that here. Okay, the last one is prop. So that means that the last layer in AlexNet is called prop, and is producing an output that is also called prop. We will see this later when we see how to define a network. Okay, so after doing the evaluation of this image, so basically the evaluation is doing a forward pass through the network, and the intermediate results and the final result is gonna be stored in bars. As you would remember, bars is where all the blobs are stored. So basically we want to check just the output, and the output is stored in the variable prop. Okay, so this command here, net.getBarIndexProp, prop, is basically giving us the correct index of the field called prop, and we use then that index to access the bar structure. Then when we have access the bar structure, we check for the actual value, so the actual weights, the output itself, the image. We store in the scores. Okay, here Well, the gather operation is something you're gonna see quite often if you work with GPUs and CPUs, because this moves context from GPU to CPU. In this case wasn't necessary because we were already working on CPU, but when you want to do these sort of things of visualizing and so on, you need to move your data back to the CPU usually. And then a squeeze is just in case there are like unitary dimensions in the output blob, like something like this, for example 100 by 100 by 1 by 60. So it's basically remove the 1. Okay, in any case, the important thing is that we have the scores. So we have the probability distribution of the image to be each of our 1,000 classes. Okay, so the probability of the image to be a dog, the probability of the image to be a cat, and so on and so on. And we take the maximum. And we also take the argument of the maximum, so we know that the maximum was in the second class or in the class number 10 or whatever, and we plot that information here. Okay, just plotting the score we got and which class it was, and that's it. It's pretty simple code, right? Good. So we can continue with the session. We're gonna move to training now. We're gonna see how to do training with LeNet on the MNIST dataset, which is this classical database of digits, handwritten digits. For that, it's gonna load LeNet first. Sorry, MNIST. So if you wanna see, so I'm not gonna talk yet about the structure of an IMDb. So IMDb stands for image database. There will be a session to explain this, but if you wanna check the structure of this, it basically contains to fill images and meta parameters, and within images you have data mean, labels, and set. Data is where the images are actually stored. So you see that in this case it's a multidimensional array of 28 by 28 by 1 by 70,000. So that means that we have 70,000 images, grayscale images of 28 by 28. So we can have up to one of them. First one, yeah, that's a 5. Then in set is a vector that contains an integer per each of these 70,000 images, saying if it belongs to training, that means a 1, or to validation, which is a 3. Finally, labels basically says the class of the image. In this case, the first image, which was a 5, belongs to the class 6, and the class 6 is the class represented by 5s. Because usually we skip class 0. Class 0 means void or no information. We don't know anything. So the 0 is gonna be class 1, the 1 is gonna be class 2, and so on and so on. So just remember, skip the 0. The 0 means I have no idea what this is about. Okay. So we have loaded MNIST, and we're ready to start the training of a LeNet architecture done by LeCun. So basically we're gonna call the LeNet train code with the IMDb of MNIST, and the intermediate results are gonna be written to results/LeNet experiment 1. Okay. If we try to run this code, it's gonna fail immediately. Oh my god. Yeah, so I'm gonna tell you why. So basically, if we go to the code, let me train. One of the first thing we should notice, oh, let me check this, I don't like to, yeah, I don't like text wrapping for code. So, is that GPU option is activated, is enabled. So if we are using CPU, we need to remove that, leave it blank, we can try again. Yoo-hoo, it's raining. So basically here we see like the number of the current mini batch being processed, like 80 out of 600, 90 out of 600 and so on. How many images we are able to process per second, and then we have statistics of the error we have selected for the network and the objective function we have selected for the network. Okay, let's gonna try to understand this better by having a look to the code. So here, this is for training, and when we finish the 600 mini batches of training, we will start doing validation, and that will be the end of the first epoch. Then we will move to the second epoch, and we will repeat the process, training and validation, and so on and so on. So let's have a look to the training code. So the training code starts by calling the setup of MatConvNet. Okay, this is important. So as you will remember, this is basically to add everything to the path, MATLAB path. Then we have some basic options. So for example, that we want our mini batch to have size 100. It's quite a large mini batch. It is important to select the size of the mini batch properly. So for example, when you're using the GPU, you're not going to be able to put here the number you want. So you can't go too high because you are not going to have enough memory on your GPU to store a big mini batch. In this case, the images of images are quite small, so it's fine to have 100 images. In any case, we usually have more RAM memory than GPU RAM. So also take in mind that having large mini batches usually leads to overfitting. So it's usually better to have small mini batches creating more noisy directions. So when you perform optimization, you're adding sort of noise to the process, and that helps a little bit in the generalization, unless in my experience. So yeah, try to take that in mind. Then we define the termination condition. So the number of epochs is going to be 20. Okay. The continue option basically says that if you, for example, we have finished epoch 1. If I stop it with Ctrl+C, I don't have to run it again from scratch. So if I call this code again, it says resuming by loading epoch 1. Yeah, and it's training epoch 2. That's quite cool. Okay, this here is just to check if we have GPUs and how many. In this case, it's nothing. And here we have the definition of the network. It's quite simple and straightforward. Let me go through it. So the first thing we do is to create an empty DAGNN object. Okay. Bear in mind, this is not a MATLAB structure. This is a MATLAB object. That means this is going to be passed by reference. So every time you pass this object to a function and you modify it within that function, all the changes are going to be seen in all the scopes. Okay. Then we start adding layers by calling the addLayer method. The addLayer method requires like a name for the layer, in this case comp1, the object of the layer itself. This is the object. Let's gonna skip the object so far, and then the input for that layer and the output for that layer. Plus, if the layer has parameters, as in the case of the convolution, we need to indicate like the names for storing those parameters. Okay, in this case, the first convolution expect its input to be input. Probably you remember that before when we were doing inference, we were creating this cell array with the data, and the name of the data was called input. And this is the reason. The reason is that we say here that the first input is going to be called input. Then the output of this convolution is going to be called convolution 1, 2, the same name as the layer, but you could select a different name actually. So now let's gonna focus on the convolution object. So there are several predefined type of layers in MatConvNet, and convolution is one of them. Okay. In order to declare a convolution, you need to specify the following parameters: size, which is gonna be the spatial, the dimensions of the convolution of the kernels. So it's gonna be, this convolution is gonna consist of 5 by 5 kernels. You're gonna expect one input channel, so in this case grayscale images, and you're gonna produce a mapping to, you're gonna have like 20 filters, 20 kernels, or which is the same, you're gonna produce an output blob of 20 dimensions. Okay, so this has bias option is set to true, which means that this linear transformation consists on an multiplicative factor and an additive factor. So then we have the stride of the convolution set to 1 by 1. That means that when we are doing when we are filtering the signal, filtering the images, we are not gonna skip any pixel. Okay, and just proceed with the standard sliding window thing. And the padding variable. So this padding means like when we get our input, if we need to do some previous padding to the image. So basically these are the number of rows you're gonna insert from above, the number of rows you insert from the bottom, the columns you insert from the left, and the columns you insert from the right. And this is gonna be columns set to 0. So that's the most basic padding possible. And this is useful, for example, in case you want to keep the size of the input images, because remember that usually when you apply a convolution, if your convolution has spatial dimensions 5 by 5, the output images is going to be a bit smaller. Okay, due to that the convolution can be applied to the filter, to the pixels of the borders. So if you want to keep like the original size of the image, so you need to add some padding. It might also be useful in case your images are too small and you want to do a very deep network. So in order to let like the last convolutions to operate on a big enough area, you need to pad like the input or the intermediate results. Okay. So that's everything about the convolution. Then we have pooling. Okay, in this case, for pooling we have no parameters, as you can see here. Just inputs and outputs. Okay, it takes the input from convolution 1, which is exactly the previous output, and the output of this new layer is going to be pool 1. Okay. So the parameters of the pooling are basically, the option of the pooling are basically if we want to do max pooling or average pooling. In this case we are doing max pooling. The pool size, so the window to select the indices, in this case are 2 by 2 windows, and the stride. So pooling is going to be reducing the size of the blobs. Okay, the spatial dimension, so width and height, not the number of filters. I mean, not the number of channels. In this case, it's gonna reduce the image by 2 in the vertical direction and in the horizontal direction. Then we have another convolution, which is consisting of 5 by 5 kernels. Is expected to receive like 20 features, 20 channels. See that this matches this number. It has to match this number, and it's producing 50 output maps. 50. So again, we can say we have like 50 filters, 50 convolutions, or the same, that the output blob is going to consist of 50 feature channels. So again, we have bias, the stride is 1 by 1, we have no padding, so everything's perfect. And here we have convolution 2f and convolution 2b to store our parameters. See that there is no padding here either. That means that since our kernel is 5 by 5, the output image is going to be a bit smaller. Then another pooling, so we have already seen how to do this. Convolution, see, this time is 4 by 4 convolution, and we move from 50 features to 500, so we have 500 filters, which is the same. The output block is going to consist of 500 maps. And the ReLU, the rectifier linear unit, our first non-linearity. In this case, ReLU has no parameters either. The only thing we need to indicate is like the input, the output. The input is just the previous output, and yeah, and this is going to be the new output, ReLU 3. And this is pretty much the end of the network. We now move to the final convolution, which is going to serve as our classifier, as our linear classifier. Okay, it's declared in the same way. So basically it's going to be a 1 by 1 kernel. That means that it's going to be acting at the level of each pixel. And yeah, we move from 500 channels to 10 channels because we have 10 classes in MNIST. So this has bias 2, straight 1, no padding at all. Yeah, the output is called classifier. Then, so in order to convert the output of this classifier into probabilities, we use softmax. Okay, softmax has not parameters either, so just inputs and output. And it's very important, and the output is called prediction. So prediction is one of the predefined networks, predefined keywords here. So that is used in the training code. So the training code has some visualization features, and the visualization method is expecting like the result of this we call prediction. In any case, this is something that can be modified through the code, so that's fine. Then we have our loss functions. So we have a loss function for training, okay, and then the next loss function serves just as a metric for computing additional statistics. So it's not used during the training. So the loss function used for doing the optimization during the training is the one which is called objective. Okay, this is something that is encoded in the training algorithm. If we change it inside the training algorithm, we can change it here too. We just need to be consistent what is happening within the training algorithm. So the loss function in this case is cross entropy, or basically the logarithm of the probabilities coming from the softmax. See, this is the first time that you see that the input of a network, of a layer, receive two inputs. And this is something nice we can do with DAGNN networks. This layer can receive two inputs, but many other layers can receive two inputs too. So basically, we receive the prediction, we receive our prediction, the labels, okay, and we compute the loss out of those things. Then we added this additional loss function, which is basically a classification error. Okay, this is one of the predefined types of losses within MatConvNet, and we use this just for computing some interesting errors for some tasks. Again, we receive our prediction and the label, and basically we produce an output called error. These things are gonna be used later for visualization, as you can see here. Okay, this is how the training is going. Okay, in the left we have like the error for training and validation, like blue and red, and the objective. So does it sound familiar to you? Yeah, the cross entropy error magnitude in green and sort of light blue. In the right we have the same but in logarithm scale, so it's easier to see sometimes. And we see that the error is decreasing. The training, at least the training error is decreasing. Okay, it's also decreasing for validation, but not so quickly. And our objective is decreasing too, which is quite important. So the network is converging, slowly but converging. So this is it. This is how to define a network. It's quite easy, right? So now we need to indicate how to initialize the network. So basically I have created a small routine for this that receives the network, a weight, okay, in this case 1/100. Basically what it does is to, well, first of all we call the initialization members of the network, which allocates the memory for the different layers and so on, and also try to pre-assign some random values according to internal policies. But then I go through the all convolution layers. Okay, well, I go through all the layers and I check if they are convolution. In case they are convolution, okay, I check where the parameters of the convolution are stored, like filters and biases, and I'm gonna initialize a Gaussian distribution for each of the convolution layers. It's gonna be zero mean, but its standard deviation is gonna be f, so 1/100 in this case. Okay, this has proven to be good enough for MNIST, but for other networks the initialization has to be more complex, like following Glor's method or Hare's method or whatever. We'll talk about this later. Then I initialize each of the filters with this Gaussian distribution, and I'm on the same time we're gonna also assign like local learning rates for to these layers and weight decay, and we repeat the same process for the biases. You can assign a different learning rate to the filters and biases, and that's quite cool. In any case, the actual learning rate is gonna be the multiplication of this local learning rate and this global learning rate. By the way, this learning rate doesn't have to be a number. You can set up a vector like this, for example. So the meaning of this is that during the first 100 epochs we're gonna use 0.001 as the learning rate, and during the next 200 epochs we're gonna use 0.1 as the learning rate. If there are more epochs that learning rates in the vector, then MatConvNet just takes the last one, and that's it. Okay, so we have defined the network, we have initialized the network here, and the last thing remaining is just to call the training. So basically for that we call CNN train DAG, okay, with our initialized network, the IMDb, so the dataset we have, a call to this function called getBatch. We will talk about that right now. The options we have defined, and we select which are the images we use for validation. Usually the convention is that so those are the images that has set equal 3, so they belong to the set 3, which is the set of validation. So let's have a look to the getBatch function, because it's quite important. So the getBatch function is the function, or it's like the interface with our data, with our IMDb. So the training method is gonna call this function to ask for more data whenever it needs to generate a new mini batch. So basically the network is gonna say, hey, you told me that you want mini batches of 10 images, so please give me 10 random images. So the batch here basically consists of like a set of random indices, okay, and getBatch is in charge of like going to look for the images corresponding to those images in the database, and then out of those things create a cell array, okay, with the images and the labels. That's it. It's quite simple for this problem, because we can have the whole IMDb, the whole dataset in memory. But for those problems that like for example when we are training on ImageNet, we can't have full images in memory. So the getBatch function gets more complicated, because basically the IMDb is different. It's just consisting on names and paths and images and references. So the getBatch method has to start like preloading things, normalizing things, and so on. In this case the IMDb contains the images already normalized, scale, and so on. But otherwise the getBatch function can get quite complicated. We will see examples of these like in next sessions, but that's it. So this is how we define a network. It's quite easy, and then we initialize it, okay, and we call the training method, and we see that this thing is converging. So and the objective has also been reaching 0. So basically, yeah, the network is like converging. I'm gonna stop it. Okay, if we continue with the tutorial now, it's time to do some inference with LeNet. So since perhaps you haven't enough time to train your network, I have provided a pre-trained LeNet network, and we can load it. Okay. Remember that we need to convert it to the DHENN structure. Oops, sorry. In order to do the inference, we need to copy the metadata from the IMDb to the network. In this case, for the LeNet, the metadata was stored in the IMDb. Okay, ready to go. So, okay, what we're gonna do is, since the images are already pre-processed in the IMDb, we're gonna exploit that fact. We're gonna select the validation images. So the network has not used those images for training, just for validating. Yeah, these are the indices of the images used for validation. We're gonna do inference with some of these images. Oops. Sorry. So here we have a 4, and it says that this is a 4, which is the class number 5. It's quite confident. 1 is actually overconfident, and it says, hey, I think your number is a 4. Yeah, cool. Okay, we can repeat this process. Sorry. Yeah. We can repeat this process, like changing this. 7. Yeah, I think your number is a 7. Ooh, amazing. I think your number is a 1. Yeah, you can play with this for a while. So here you see that, like, in the background there is like a sort of 3 or 8 and 3 or whatever. This is actually due to the normalization of the dataset. So probably the 3s are more abundant in the dataset, and that's why the mean has to do with the 3. But in any case, the network doesn't get confused by that. Yeah, it is still recognizing digits very accurately. Okay, let's gonna do something cooler now. So what if we check the activations of the network? Okay. Oh, by the way, the code for inference for the net is pretty much the same code as we saw before for AlexNet. The only difference is that in this case, since we are not using external images, we're using images coming from the IMDb, which are already pre-normalized and so on. I have like disabled the normalization options, so that's it. I'm just converting the image to single, but it's even unnecessary here because the image coming from the IMDb are already single, so yeah, it should be fine. The only difference here is that I'm using this special flag called conserve memory. This is a very important flag in MatConvNet because basically it's telling the evaluation method if it has to keep the intermediate results or not. So basically, if conserve memory is equal to true, MatConvNet is gonna try to like save a lot of memory. So that means it's gonna destroy all the intermediate results. If you set that flag to false, then all the intermediate results will be kept. This is interesting and important if you want to check like intermediate activations, which is what we are gonna do right now. So here, since we call the inference script with the option set to false, MatConvNet was like keeping the intermediate results, and now we can check the activations. If you remember, I told you that a bars contains all the blobs. Okay. The first blob is the input data itself, and the second blob is the first convolution, the output of the first convolution. So why don't we check like the activation of this image, this one, when passing through the first convolutions. So for that, we're gonna check the different filters of this first convolution. So we're gonna check filter 1 and filter 2 and see how they look like the outputs of these two filters. Okay. So if you actually go to the filters, like using the visualization code we saw at the beginning, I have a look to the first and the second kernel of the first convolution. You see that their shape is quite weird. So they are focusing on like specific shapes, and that's why probably the activations look like this. So why don't we do that actually? Why don't we go and visualize the filters and try to make some sense out of this. I can't promise anything, but so I think we can stop this already. Yeah, it looked like a shape. So the first filter, it's sort of correlating with things that are like in the middle and the upper right area. And the second filter, okay, the second filter actually makes more sense. Actually, I don't see why. So yeah, I see why this part correlates, because yeah, this would be more or less here. Okay. Yeah, this part matches more or less this part. That makes sense. But then, yeah, this part thing doesn't fully match this shape. Anyway, for the second one it makes more sense because it's like focusing on the sides. So these high activations here are probably activation to the white areas. Okay. And then the number itself in black like matches this thing, and I mean this might have some sense. I don't know, it's a bit hard. Let's visualize the third one just for fun. Yeah. Well, I'm tired of playing this game, so if you come up with a nice explanation why these responses are matching these filters, just please send me an email. I will be very happy to hear about that. Okay, yeah, this was the end of Lunet. So now we're gonna do the last cool thing, which is we're gonna try on AlexNet, which is one of the most famous architectures ever on Cypher 10. So for that, we're gonna load the dataset. Okay, I'm gonna close the eyes. We load Cypher 10. So Cypher 10 is a collection of small images coming from 10 different classes, like cars, planes, so on and so on. Actually, yeah, so airplane, automobile, bird, cat, deer, dog, frog, horse, sheep, and truck. Yeah. So these images are quite small, like 32 by 32, and we have 60,000 images. So 50,000 for training, 10,000 for testing or validation. Okay. So now we're gonna do training on AlexNet directly. But like before, we need to remember to remove this because we are not using GPU in this example. And this is going to take forever in CPU. So we are processing the third minibatch out of 500. The objective is starting to move slowly and like oscillating a little bit. But well, it will get better step by step. Yeah, it's normal to see this sort of small oscillation at the beginning. The thing is that if you move to GPU, this thing passes very quickly. You don't even notice it. So this is the code for training with AlexNet. So it's pretty much the same as before. The only thing we have changed, we have added weight decay. Okay, we'll talk about weight decay in the next session. We have momentum. Yeah. But well, the way to initialize the network is sort of the same. We have changed the initialization a little bit. I will explain now why. But let's have a look to the network itself, because there are some peculiarities here in AlexNet that I would like you to know. So, but before that, let's see how this goes. So, okay, the error is decreasing or oscillating, and this is slowly moving down. Yep. So I have stopped the video for a while to show you how the network is actually converging if we wait for a couple of millibatches. So now it's 2.25 and going down slowly, but going down. Although in GPU this is much faster. In any case, going back to the definition of AlexNet, so it's pretty much the same everywhere. The only difference, AlexNet starts by having this convolution which has 11 by 11 kernel size. Now we have RGB images instead of grayscale. We produce 96 filters. Okay. Here we see that the first convolution of AlexNet has stride 4. Okay, so we're gonna skip like 4 pixels. We have to, so this is not in the original definition of AlexNet. We have to add this padding to the CFAR images because the CFAR images are very small, are 32 by 32 as we saw before. Okay, then this is followed by a ReLU. Okay, and this layer is local contrast normalization. So these are some fixed parameters of the operation of local contrast normalization. And are basically indicating like sort of shift, some multiplicative factor, a gamma correction, and so on. If you want to know more about this transformation, you can go to the folder MATLAB. Okay, and here you have like the basic layers. So if you go inside normalizing, so you can check the actual definition, or else you can go to the MatConvNet explaining how each of the layers is working. So the local response normalization or local contrast normalization has is taking the input, okay, squaring it, then you have this alpha, which is the scale factor I was saying, this shift on this exponential, so this beta. So this is what the local contrast normalization is doing. and it can be applied to group of channels or to individual channels. So this is indicated here. You select how many channels you want to group. Anyway, we will explain more about the different layers like in next session. So the local response normalization is followed by a pooling. Okay, then we have convolution again, but there is something weird here if you have a close look, because usually, so the previous convolution was producing a 96 an output blob which consists of 96 featured channels. So the input of this second convolution should be 96 and not 48. But MATLAB has a special MatConvNet has a special feature called well, it's a grouping of the channels for the convolutions, and this is probably just useful for networks like AlexNet. So if we check the paper of AlexNet, and we have a look, we see that there are like two different flows. So the network divides in two. In order to do that, MatConvNet has implemented this mechanism, which consists on that you can indicate as the number of input some number that can divide the previous output. So if you were expecting 96 inputs, you can indicate 48 because 48 is half 96. Which this means in practice is that you're gonna take the 96 outputs and you're gonna create two independent groups out of them. Okay. Then you're gonna dedicate half of your convolution, half of your filters to the first half of the signal, so to the first half of the channels, and the second half of your filters will be dedicated to the second half of the input channels. So basically you're doing this sort of splitting in order to have like 2, 3, 4 or 5 groups. I hope the concept is sort of clear, but I don't know if perhaps we should write it down somehow. This is called improvisation. So for example, in this case 96, so you have, can I copy this? This is layer 1. This is layer 2. Okay. One, so convolution 1, sorry. Convolution 2. Let's gonna ignore redos and normalizations. So imagine I have this input, which is basically I don't know, 32 times 32 times 3, and my minibats is like 10 images. Okay. Then after convolution 1, I will have something which is like, if we ignore like the strides and so on, we will have something that is like 32, and assuming that we have added some padding, and now 96 times 10. So convolution 2, okay, should be something like this in order to match this input. So the number of feature maps of the blob. what is happening here is that this blob okay, imagine you have convolution 1, which is 11 by 11 by 3 by 96, and convolution 2, which is 5 by 5 by 48 by 256. Okay, if we assume our input is like 32 times 32 times 3 channels times 10, so we have a mini batch of 10 images, this is what is happening. So then after C1 we have a blob which is gonna be like imagining that we ignore paddings and we ignore relus and everything, we will conserve the spatial size. Now this is 96 times 10. Okay, and this goes to C2. Okay, but C2, the second convolution, should be matching this 96 here, because the input blob has 96 channels. So this will be 96 in order to make some sense. What is happening here? So what MatConvNet is doing is taking this blob and is like considering two parts, two groups of these channels. So if we have 96 channels, the 96 channels are divided in two groups of 48. These two groups of 48 are processed independently by the second convolution. And finally the second convolution is producing this 226 dimensional blob. So the result is gonna still be the 226 thing, but the different input channels have been processed independently by the different filters of the convolution too. So in this way we can simulate this sort of AlexNet architecture. Okay, and this is the only peculiarity of the convolution in AlexNet training. Okay, this thing is repeated a couple of times. For example, here it should be 384, but it's 192, and so on and so on. So see, I would like to talk about fully connected layers. Okay, because many people think that fully connected layers are something special, but fully connected layers are convolution too. So you can define a fully connected layers basically by defining a one by one convolution. Okay, so we can talk more about this in next sessions if there are doubts about this concept. But yeah, so what is going to happen is that at some point your intermediate blob, the blob reaching the convolution, is going to be small. Probably is going to have a spatial size 1 by 1, and then so you are already seeing the whole context of the image. That's why everything gets fully connected. It might also happen that at some point your blob is like 6 by 6. Then if you do a convolution which is 6 by 6, at the end you're gonna get like, and you don't add any padding, at the end you are sort of correlating the full context of the image with this filter. So that's also get fully connected. Okay, so in general fully connected layers are convolutions. Good. So we have a couple of fully connected layers that are simple convolution followed by relus. We end up with our classifiers, again from whatever number of dimensions to 10, because we have again 10 classes. Then we have softmax. Okay, our objective loss, which again is a cross entropy loss as before, and our classification error, just to have some extra statistics to solve. Everything else is as before. The only difference is in the initnet code. I have to change this piece here. Before, all the convolution layers were initialized in the same way by using the 1/100 factor to initialize the Gaussian, so the covariance of the Gaussian. But this case was different. So if you try to initialize all the layers in the same way with 1/100, you see that the network gets completely stuck. It doesn't converge to anything. The reason is basically that there is this problem with the gradient getting vanished, so vanishing gradient. And in this case is due to the signal, the intensity of the signal, so the magnitudes of the input image are not so high due to normalization. So you have to do the magnitudes of the image a bit higher, or to initialize the weights a bit lower. Sorry, a bit higher for the first convolution. So that's why we have multiplied the covariance of the matrix by 10. So we are sort of increasing the magnitude of the input signal through the filters. Because at the end, since this is like a linear operation, this 10, it doesn't matter if it is absorbed by the convolution or by the input signal. But I think it's more clear if it's in the convolution. Okay. If you do the same for the remaining kernels, at the end what you get is that the networks start diverging, so you get like exploding gradient. Okay, so don't do that. You should play a little bit with these things to check what's going on. Okay, but this is it. So the networks are still converging. We are now in the validation of epoch 1. Things are going fine. So I hope you have enjoyed this first session. See how easy it is to define and to train a network from scratch, okay, in your own data. How easy it is to define networks architecture in the MatConvNet and do running even in CPU, although it takes like quite a lot of time. Well, I think it's a nice experience to check how easy it is to do these things and how many cool things can be done by a couple of MATLAB lines. So I hope to see you next week. See ya.